Okay, right. So it's an honor and pleasure to introduce today's distinguished lecturer, which is Michel Abdalla. Maybe like 2 words about Michel. So Michel holds a PhD in computer science from UCSD with Michel Abdalla, and this is actually where we met for the first time in San Diego. And after that, he went, I think, to a couple of companies, but for a long time, he's already with CNRS in France, in Paris. And he's a director of research there. So that's the highest position there is in CNRS. He's also an adjunct professor at CNRS. He's also one of the directors at the ICRs. He has been one of the directors at ICRs from the years 2013 to 2019. And since 2020, he got, is that a promotion? And he got promoted to be the president of the ICR. And he's been there ever since. So Michel is known for his various contributions to the theoretical and also the applied side in cryptography, most notably in the design and analysis of crypto systems. So he has been very active in encryption standards such as DHIS, passport authenticated key exchange, which today's lecture is going to be about. Is I think this the other topic. He's I guess one of the leading experts in the world. He recently also did some other work on functional encryption and signatures and other things. Anyway, so Michel, it's a pleasure to have you here, and I'm giving you the word for the distinguished lecture. And yeah, maybe questions. No, we just settled that. Questions. So there is a Q&A in the Zoom system. Just ask your questions, and then yeah. Michel will try to answer as many as possible in the end of the talk. Okay.
All right. Thank you, Eike, for the nice introduction. It's actually a pleasure to be visiting Bochum, even if this is a virtual visit, and the opportunity to give this lecture on password-based key exchange. As Eike was saying, like if you have questions during the talk, you can use the Q&A or the chat option. I have both open here on the side, but sometimes it is hard for me to monitor. But so if I don't answer right away, please excuse me. So as the title indicates, today's lecture, it's about building key exchange from using passwords as the means for authentication. So let's to start, like one of the fundamental problems that we have in cryptography is how to enable secure communication when the channel that is connecting the users is insecure. So in that case, usually a common scenario that we have is that we're going to have a shared secret key that we're going to use to encrypt the messages and authenticate the message that we're exchanging. And often the way the secret key is obtained is via a key exchange protocol. So since we're talking about key exchange protocols, the most well-known protocol in this case is the Diffie-Hellman protocol, in which you assume a cyclic group G, typically often you assume it to be of prime order, with a generator G, little g. And then the protocol works is very simple. For each party chooses a random element in ZP, and then computes G raised to that secret element. And then they exchange these values. So by doing this, they both, for instance, in this case, Alice and Bob, they both can compute a common key, which is G raised to the product of the 2 secret elements. In this particular case, they're named X and Y. So it's a very simple protocol, but it's extremely nice because it enables to compute a key without and if somebody is observing the communication between Alice and Bob, that person will still not be able to figure out what the key is by just looking at the messages that were exchanged. Unfortunately, why this works for passive adversaries, this protocol clearly does not provide security against active adversaries because the messages are not authenticated. So Alice, instead of talking to Bob, it could be talking to someone else, and he would not know the difference. So for that reason, like the goal that we really want to achieve is to have an authenticated key exchange, or AKE. In that setting, the goal is to establish a common secret, but in an authenticated manner. And in order to be able to do this, somehow the parties that are being that are trying to establish the key should have some method to authenticate each other. Is that what we call implicit authentication, meaning that the session key that the parties will compute at the end should only be known to the parties involved in the protocol and not to anybody else. And like in the security proofs of these protocols, usually what we prove is that the session key that is generated by these parties they are actually indistinguishable from a random string in the same domain. So before we talk about how what is considered secure AKE, it's important to also know how they are used. So in practice, you're going to have two phases. The first one in which Alice and Bob, perhaps they will rely on some trusted parameters. They will run the AKE protocol to compute a joint key, SK. And then later, they're both going to use this the SK to secure their communication. And it's important that in order for the AKE protocol to be as useful as possible, you should not make any assumption about how the secret key is used. So in particular, sometimes in some cases, the users using these keys, they will not be as careful as other users, and they may actually leak the key because it perhaps just can leak by sending that in the clear or by using a bad encryption mechanism that leaks the secret key. There are several different ways in which this can happen. But the important point is that there is a chance that this will happen. And if one user leaks the secret key, it should not have an impact on the secret key of other sessions. So in order to achieve these goals, there are several authentication techniques commonly used in practice. So the typical one that we use assumes the existence of a public infrastructure, so a PKI. And in this case, each party in the system is expected to hold a pair of secret and public key. And so this is one typical case. And the other typical scenario is what is known as symmetric techniques, in which each pair of users actually share a common secret key, a random secret key. And sometimes in this setting, we can also consider like not only two-party setting, but it could be also a group setting, for instance, in which a group of users, or multi-party setting, in which a group of users share that secret key that they will use to authenticate each other. Password-based technique is actually a particular case of a symmetric technique in which the secret key, instead of being random, having very high entropy, is actually considered to be a weak secret. For instance, a 4-digit PIN, something that it's not very long, that in principle, there is a chance that it could try out in practice all those, enumerate all the secrets. So because of the secret is considered very weak, these protocols are always subject to what we call online guessing attack. And in this case, and why is that the case? Let's, and sorry, which I would talk about it later. And the reason for that is because the adversary can always, since the number of secret values, possible secret values is small, the adversary can always guess. And I will, as I said, I will give an example, a more detailed example later. So, but before we can get to that part, just a quick example of a PKI-based technique. For instance, since we are talking about the Diffie-Hellman key exchange, we can see an authenticated version of that key exchange scheme using signatures here. So this is the signed Diffie-Hellman protocol. Another one, the same thing being authenticated using symmetric techniques. In this case, we assume that the secret key K will be used as a message authentication code key. And here we have the authentication is done using a MAC. So, but as I said, what about password-based authentication? The nice thing about password is that it's very realistic in the sense that, like in real life, often people actually rely on weak passwords. So sometimes we can have our computer generate some of the secret keys that we use for authentication, which might be a very long one. But eventually, like the security of these systems end up relying on the password that you use to log in onto your computer, which itself probably is not always very strong. So that's why in reality, we have to consider the case of passwords because it is something that people use in practice. And the reason people do that is because passwords is something that you don't need to store to write on a piece of paper because it's too long to remember. It's something that you can actually memorize and use it every time without requiring any special type of hardware. But as I said before, it comes at a cost that these protocols are always subject to online guessing attacks. And what are these attacks? As I said before, like let D represent the dictionary or the set of possible passwords. In this case, online dictionary attack is something very simple. You just choose a password from the dictionary here, and then you interact with the server using the password that you guessed. And because the set of the size of the dictionary is usually small, here the probability of success is going to be 1 over the size of the dictionary for every attempt that you have. And this is one case where if you use a symmetric, like a high entropy key, the size of the dictionary is very large. So this will not be an attack against a typical symmetric key based technique for authentication, but against passwords, it is a very effective attack. So because of that, one countermeasure that we usually have is that once you fail a certain number of times, usually you're going to find some limit in the authentication. You will not be able to keep trying. So what is the goal of password-based authentication? It's to show, like, since dictionary attacks are not, online dictionary attacks are not possible, the restriction is to actually make sure that this is the only possible attack that the adversary can have against the system. So for the remainder of the talk, I will like first give some background on on the security models for PAKE and the different types of PAKEs that we have. Then the rest of the talk I will go over first some PAKEs based on ideal models like random oracles or ideal ciphers. And then I will give you, we'll also cover some examples of password-based key exchange in which you don't make these idealized assumptions. Finally, I will very briefly discuss, mention the candidates of the CFRG PAKE competition. I will already be covering some of them here in the ideal model part. And then I will conclude with some general remarks about the area. So as I said, like in this setting or in crypto in general, like several protocols, sometimes they are only proven based on some ideal assumption. For instance, the most typical case in which we consider is the random oracle model, in which a hash function is modeled as a perfectly random function. So as I said, here is perhaps one of the most used models in cryptography, and it's actually most of the standardized schemes that we know of actually rely on have security proofs in the random oracle model. Another model that is sometimes used in the security proofs is the ideal cipher model, in which here, like you can assume, it's like you're modeling a block cipher such as AES as a truly random permutation. And this is like for each key, that for each possible key that they behave as a truly random permutation. It's an extremely strong model, but actually there are some relation between the two that have been proven. Finally, the other model that we assume here is the standard model, in which you don't make any of these idealized assumptions, but you may actually rely on some trusted common reference string or CRS. This is the case of some of the protocol that we're going to see here in this presentation. Finally, we have plain model, which you don't make any type of trusted setup assumption. I think since we're talking about password-based authentication, it's also important to make a distinction between what type of protocols we're considering here. Like in the literature, you see two types of password-based key exchange, which is called balanced or augmented. In the balanced case, which is the standard PAKE, I would say, is the one in which all the parties, they actually share the same password. Like the parties establishing a key, they share a password. So if it's the two-party setting, like consider Alice and Bob, they both will share some password between the two. In a group setting, this could be a group password, but like different pairs of users should be sharing different passwords. And then there is the augmented version, which is also known in the literature as verifier-based or asymmetric PAKE. And in this case, typically we're talking about the two-party setting, in which one of the party actually knows the password, and the other doesn't know the password itself, but just something that allows it to verify if it's talking to the right person. So he only holds a verifier, VF. But this verifier is specific to that password. So, and in particular, if it's something that the user could recover, it allows if you have the verifier, in principle, you can recover the original password from using that verifier, but in an offline manner. Sometimes if the password is really chosen in a bad way, this can be a very easy search. But if the password has high entropy, then this process actually may be expensive. And finally, what is a secure PAKE? the idea of secure PAKE is essentially similar to a secure key exchange, in which you assume that users can run several protocol instances in parallel, so in any order possible, and that they will give complete control to the adversary for the communication network, meaning the adversary in principle can start new sessions between users, modify messages that are being exchanged between users, or simply forward those messages. And in order to capture the security in practice, you also have to assume that some of the users can actually be corrupted, or some of the session keys can actually be exposed by accident. So the adversary should also be given these capabilities in the model. And the goal of secure PAKE is to show, as I said before, that online dictionary attack is the only one possible. And what is interesting here is that like passive eavesdropping should not help at all, because in a passive eavesdropping, the adversary will not learn any information about the key. And for the active attacks, the goal is to prove that the adversary can try at most one password for each active session. So essentially, the success probability of the adversary should be something like the number of active sessions over the size of the dictionary, plus some negligible term. So, and in addition to that, actually, there is a more general definition that was proposed by Canetti et al. In 2005, which proposes a definition in the UC framework. The only reason I mentioned this here, I will, like some of the proofs that in the literature that we talk about here are in the UC framework, but I will not actually go over those proofs here. But what is interesting about is that one of the aspects that make the UC security definitions very appealing is that the definition makes no assumption about the distribution of passwords. In particular, the passwords can be related. And consequence of the UC framework is that once you prove security, that security is preserved under arbitrary composition. So in that same paper, the authors also proposed a new protocol that was able to, whose security follows from standard complexity assumptions, but at that time the scheme itself was not as efficient as all the other protocols in the game-based models. So now that let's finally get to some of the big schemes. So I will start with some of the constructions in the ideal model. And so the first work actually in this area is known as, it was by Beloved and Merritt in 1992, known as encrypted key exchange. Like it was a very interesting work, but they did not provide any proofs or security models. But the idea was quite appealing and attracted a lot of attention in the literature. Like at the time, some of the work, there were several follow-ups, but not necessarily secure protocols that were proposed. But one of the interesting follow-ups was by Jablon in 1997, what is known as SPEKE protocol, SPEKE, which is similar to the Diffie-Hellman key exchange, but the idea is that instead of using a public generator, you're going to use the generator as hash of the password. So it's a very simple protocol in that respect. And then in the early 2000s, there were several instantiations of the E-key protocol in the random oracle model. Here I mentioned a few. I will talk about them quickly after this. And sorry, the same line got repeated that I shouldn't, I forgot to remove. And then later in 2010, another interesting protocol that was proposed is the J-PAKE protocol, like a password key exchange by juggling, using juggling techniques. That's how they refer to it, which is also a very reasonably efficient protocol. And one of the features at the time that attracted a lot of attention is that it was free of patents, which was an issue with all the previous schemes that I mentioned up to that point. This is no longer the case because those patents have expired, but at the time it was an important issue. And then more recently, there was the CPace protocol that, which is a implementation-oriented version of SPEKE that makes a lot of improves SPEKE in a lot of details to make sure that, like, to implement it in a way that is actually secure and take into account other things like side channel resistance and the fact that here you have it requires a hash to the group, hash to curve operation, and CPace considers ways to implement this in a faster manner. So what is the encrypted key exchange protocol? As I said, the idea is extremely simple. This is essentially the Diffie-Hellman protocol in which you encrypt the flow, the two messages using the password. So there is nothing more than that. Like here you see, all you do is you encrypt the message X using pi. So if you know pi, you can decrypt it and easily and compute the key as you would in the regular protocol. And then to derive the session key, you just compute a hash using the messages that were exchanged. So sorry for here, this should have been bold. This should have been in bold because is the transcript messages that were exchanged that should be included here, plus the key and the password. So it's a very simple protocol, but can it be proven secure? And actually there were a few ways in which this protocol was instantiated. First, in BPR 000, Bellari, Poincheval, and Rogway, and then Bresson, Chevasieux, Poincheval in 03, the encryption function is just treated as an ideal cipher, and the age function is treated as a random oracle. Then Mackenzie 02 and again Bresson, Chevasieux, Poincheval in 04, they have a similar proof of this scheme in which they instantiate the encryption function as a random oracle and age as also as a random oracle. And then now work by myself together with Poincheval, we actually showed that the encryption function can be a very simple function in which you assume that you have a generator age for which you don't know the discrete log. So this is it would be a part of the trusted parameters. Then the encryption function is just X times age raised to the password. And age is still modeled as a random oracle. Sorry for that. Then, so this is what I mean by that, the simple PAKE here. So this is the protocol, and in the PAKE, we actually called, in order to get reduction to the computation Diffie-Hellman protocol, we used a different generator in each direction. So we used M in one direction and N in the opposite direction. But you can still prove security if M equals N, but in that case, you have to rely on the square Diffie-Hellman problem. And then once you do that, why is this protocol secure? So as we showed in that paper, if you assume that the computation Diffie-Hellman problem is hard in the underlying group and age is a random oracle, we actually show that this is a secure against active attacks. By the way, this proof here since I'm not going in details, here I'm not talking about corruptions, because if you consider corruptions, you actually need a stronger version, which is the gap version of the computational Diffie-Hellman problem, which I will not mention here because we're not going into details. So what is the intuition? For the security itself is actually not that hard to prove, but essentially the proof of the protocol consider two cases. Of course, if you look at the text details, the first one is first proof for passive sessions. And for passive sessions, actually extremely easy to prove, because here you assume that the adversary is just forwarding messages. So in that case, you can see that even if that adversary knows the password for those sessions, it still can have no clue whatsoever about the secret key that those parties will compute. Why is that the case? If the adversary knows the password, then all it sees eventually is X. It can compute X, it can compute Y, but then in order to be able to distinguish the session key from a random key, it has to compute K. And K is exactly the CDH problem here. So that's why in this particular case, security is very standard. It follows from the computational Diffie-Hellman assumption. What about active sessions? That is slightly trickier, because as I said, the goal here is to prove that you can guess at most one password for each active session. So how do we do that? The idea is to show the attack can compute K for each session. That like, let's say here a session in which the adversary is being active, is playing the role of Bob against Alice. The adversary is gonna see some X and it's gonna send some Y. And then what we're going to show is that the adversary can probably compute the key K for at most one of possible value of the password. And the way we do that in the proof is actually simple. In the proof, we simply simulate Alice without the password. We just choose X at random, for instance, as M to the X. In the latest proof, or you can just assume it's G to the X. And then when Bob receives a message, we don't know how to compute K because we don't know the password here. So then we just set K to bottom, but we choose the session key at random. So how can we prove that this is the argument here, that at most you have one password guess per active session? The idea is that if the adversary guesses the right password correctly, you will know how to compute K. But the way we're going to show is that the adversary can do that at most for one possible value of password. So let's consider M and N to be G to the N, N to be G to the little n. And we're going to say that a tuple X, Y, K, pi is valid if K, the value of the K is the correct one. Since here I had to compute, put X minus pi M, because in the simulation, we just simulated X as M to the X, sorry. Then if we do this, the proof essentially consists of showing that the adversary cannot compute two such tuples. It can compute one if it guesses pi correctly, but it can, if it does this for two possible tuples, it will break a hard problem. And actually, this proof, the problem I don't show here is just because there is it requires a bit of notation, but it's actually a simple proof that reduces to the CDH problem. And that's why this protocol is secure against if you assume CDH problem. How about Now the other protocol that I mentioned, the SPEKE protocol. So here the generator depends on the password. So the idea is similar to what we had before, but so now instead of using G being part of the trust parameters, now we just assume that G is generated using random oracle big G of the password. And now all they do is like both Alice and Bob compute these values, and they exchange the messages using the G to the, like Alice will compute G to the X, Bob G to the Y, and the key becomes really G to the XY, where G is the hash of the password. So interesting, the proof strategy here is very similar to what the proof of SPEKE2, SPEKE, but in order to prove that the security against active attacks, we require a different type of assumption, which is known as simultaneous computation Diffie-Hellman. And the assumption is stated here and was given but in a paper in which they proposed another protocol known as TB-PEAK. So interesting, we don't know exactly how to show that this assumption is related to the standard CDH, but it seems to be like if you consider generic groups, this is an assumption that seems to hold. And this is enough to prove the security of the SPEKE protocol. As I said before, the CPace protocol, which is an implementation-oriented version of the SPEKE protocol, will also rely on this assumption for the security proof. So, as I said, another protocol. The reason I mentioned these three is that, like SPEKE protocol can be seen as a particular case of the encrypted key exchange protocol framework idea. Then you have the SPEKE, which covers another set of protocols, and finally you had a third type of protocol, which is like by its own on its own, which is the J-PAKE. And in this protocol here, it seems slightly complicated at the beginning because you exchange a lot of messages. But if you forget, like here, the protocol starts, let's consider present slowly. The protocol works by, like, Alice would choose two random elements in the group, like it's going to choose x1, x2, and then compute G to x1, G to x2, and send that to Bob. Here, in addition to send those values, for security reasons, which I will not cover in this talk, you also send proof of knowledge that you know the little x1 that associated with big x1. So essentially, this Bob would do something similar on the other side. We'll choose x3, x4, and send those values to Alice. Because you have proof of knowledge here, is like essentially, it's very hard for Bob to actually generate an element x3 or x4 that is related to the values that Alice sent. And likewise for Alice, the other way around. So this proof of knowledge guarantees that these elements somehow are generated independently, or you like the only other option that Bob could have is to replay. But even that, since you use a different label here, that would not work. So after you do this, then there is a second round in which seems complicated, but all it does is the part in which Alice and Bob will actually use the joint password. So they're gonna use this, generate value alpha, which Alice generates alpha using as the basis x1, x3, x4, and using x2 password as the exponent. And then it sends a proof of knowledge that this is correctly formed. Bob does the same on the other direction by using different values. So here the base for Bob is x1, x2, x3, and the exponent is x4 password. Finally, they both compute the key. Shape of the key here, you can see that is g raised to the product x1 plus x3 times x2, x4, and the password. So since it seems quite complicated, so if you forget all the proof of knowledge part, the reason this the key looks random to the adversary. So let's consider, for instance, an active attack in which Bob is the adversary plays the role of Bob. So let's assume here that Bob is essentially doesn't know the password, so it's gonna do this protocol here using, like, it doesn't have a lot of flexibility in the first round, so it sends x3, x4, and then when he gets to the second round, he's gonna choose some password pw prime. And because like once you do this in the proof, what we show two things. First, that alpha in this case will look random to like a random value to Bob because of the DDH assumption. Because here you see that alpha contains x1, x2 here. So it contains g to the x1, x2, which is going to look random if you consider the DDH assumption. So this is one thing that Bob see. So alpha now is random. And now, why is the key? Like if you break down the way this the key eventually gets computed, you can see that the key will contain several parts that Bob can. This part here that Bob could compute, but then you have this factor here on the key, which contains a square gx2 square factor. And if you assume the decisional square Diffie-Hellman assumption, this will look random. So that's why the key will look random to the adversary. So this shows that, like, if the adversary doesn't guess the password correctly, then eventually it will not be able to compute the key. So if it uses the wrong password, like it does this will factor here will be non-zero. So then the key will look random to the adversary. So how about the standard PAKE? There, as I said before here, I just want to give you a very, very brief overview of standard PAKEs, because sometimes proofs in the idealized models like random oracle can be very easy to understand, but we also know that random oracles don't exist in practice, and it's an idealized assumption. So can we go around that and use something that does not rely on random oracles or ideal ciphers? And the answer is yes, at a certain cost to like in terms of practice, because the schemes become slightly less efficient. So as I said, like the first protocol that was proposed in this study was in the plain model was by Goldreich and Lindell in 2001. So that was a long time ago, but it was more a proof of concept. It was extremely inefficient. Then in CASA, Stravinsky, and Young, so the COI protocol that was later generalized by Gennaro and Lindell, they proposed a very nice protocol in the standard model. And this protocol was later generalized to the UC model by Canetti et al. And then more recent, you had some other constructions like CATS, Vacuum and PAKE that can achieve the same thing, but in one round. It was a very protocol that requires 12 group elements being exchanged. Then got slightly improved when I worked by myself, Fabrice Benamudai and David Poncheval. And similar, there's a few other variants, which I will skip here, but it's just later you can, if you want the slides, later I can send you so that you can look at these references. So, but the idea of the protocol was uses what we know as multi-project hash functions. So the idea is actually, this is a very particular type of a function, hash function, in which there are two ways of computing the function. Using there is a secret way that is, if you know the hash key, the secret hash key, you can compute for any point in the domain X. Or if you know a projected key, you can compute this, but only for a subset of the points, meaning for those belong to a certain language as L in X. And the computation in this case, if you're going to compute using the public method, it requires for you to know a witness to the fact that X belongs to the language. So in particular, so you have 4 algorithms: the hash key generation that generates the hashing key. You have the projection key generation that computes the projection of the key. The hashing algorithm, which itself computes, if you have the key and any point in domain, you can compute this value. And the projected hashing, in which you use the projection and the point and plus the witness. So as I said before, here, the idea, as I said, you have the hash key generation that generates HK. You have the projection key here, the projected key, which is public. And now suppose that you have a point X that is given as input to the hash and to the projection. So for correctness, if this, the point H and H prime will be the same if X belongs to the language. And then the other properties that we have of the, as I said, the smoothness, that the output of the hash will look random if X does not belong to the language, and is going to look random, but not in a computational way if X belongs to the language and L is a hard language. So using these properties, which just summarized here, so but I will go over, we can actually build a PAKE scheme. So just to give an example of what these hash proof systems look like, here is something that relies on DDH. For instance, the language here, the points in domain are just 2 group elements, and the language here is like set of DDH tuples, where X is like things that are computed using the same exponent. So, and you can see using this that that you can actually define the hash key. If the hash key is just 2 elements, and you can compute the hash as x1 raised to the keys. So now using these tools, we can actually build a PAKE scheme using a few tools. This is what the General Lindell and the COI protocol did. First, you assume an encryption scheme that is chosen ciphertext secure, a hash proof system for the language in which C is the encryption of the message. So here we're gonna essentially, the message that we're going to encrypt in the protocol is gonna be the password, and we need signature schemes. And the idea is not that hard once you have all the tools available. So how does it work? Alice, if you in the first flow, is just going to compute an encryption of the password and send it to Bob. And then Bob, once he sees the ciphertext CA, he computes a projection key and sends a project. He computes a hash key and a projection of that key. So it's gonna use the hash key to compute the key on each side, and it sends the projection so that Alice can compute the key. And Alice will will be able to compute the key because it knows the witness, because Alice was the one that encrypted the ciphertext, so it knows RA and can use this to compute the hash. It knows the password. And so here is an example where both Alice and Bob can compute the key. But this protocol would not be secure the way it is because essentially, like Bob can always compute this for everything. So if Bob just sends a projection key here and knows the hash key, Bob could actually do an exhaustive, an offline dictionary attack if this is all the protocol does, because you can see the value of the key that Alice generated and try all the passwords to be able to compute that. Because of that, you have to do the same thing in both directions. And this is what the protocol does. So Bob also computes an encryption of the password in CB, and Alice sends a projection. This is the main idea. The protocol itself actually requires a few more things because of to avoid all these attacks that you can have in the protocol, in which you mix and match things from different sessions. So the protocol involves signature schemes, and which I will skip that part. But the intuition for the security is that if the adversary is passive, because security follows from the pseudo-randomness property of this project hash functions, and if the adversary is active, then if it encrypts the wrong password, then we know that because of smoothness of the hash proof system, the session key will look random. And because the scheme is in CPA, the adversary does not, and because we're using signature, the adversary cannot modify existing ciphertext or reuse them. Then the only strategy left for the adversary is to guess the password. So this was to give an intuition about standard model PAKE. So of course, you're welcome to ask questions later, since I went a bit faster on that one. Finally, just a brief discussion about the CFRG PAKE competition. As I said before, there were here I'm concentrated on the balanced PAKE part. So in the balanced PAKE competition, there were actually 4 candidates that were considered. There was SPEKE, which is a very efficient solution and is based on the AKE approach. So, and then the second candidate, which we also spoke today, is the SPEKE protocol, which is, as I said, in this joint work that we had at Crypto last year, we also proved security, UC security for SPEKE. As we actually prove for TB-PEAK, but the proof for SPEKE follows from that. And it's interesting to see that so both SPEKE and in the same paper, we also prove UC security for SPEKE. So SPEKE and SPEKE in that sense have very similar security. More recently, actually, we also, like in that same protocol, the proof could also be applied to CPace, but there were some, but we did this more explicitly in our recent work, in which we showed that CPace, a version of an implemented-oriented version of SPEKE, is also UC secure. So, and finally, the fourth candidate was J-PAKE. So, which was proposed in 2010 by Howe and Ryan. And like, it's a reasonably efficient protocol, but at the time didn't have a proof, and then we provided a proof of security in like about 6 years ago. And more recently, we actually showed that we improved on that proof, that we showed that this scheme is also UC secure. So just to summarize, actually, in terms of security, I would say that there is no clear distinction between any of these protocols. Perhaps like J-PAKE actually achieves a very strong notion of security, but there was one caveat, which is the actual J-PAKE protocol uses Schnorr proofs, and we were only able to show that Schnorr proofs satisfied the conditions that we needed for the proof of knowledge if you assume the adversary to be algebraic, which is in reality it's okay, but it's interesting to, like, important to point it out. And actually, we have ongoing work that shows that like if you assume the adversary to be algebraic, that SPEKE or CPace, they both actually achieve also this standard UC security. So in a way, all of these protocol variants, they provide similar security levels. And the question whether which one should have been used, it turned out to be related to other things. For instance, one aspect that was discussed in the competition was the quantum annoyance, meaning that if you break, in order to break the security of the scheme for one pair of user, you should have to be able to use be able to solve a discrete log problem specific to that pair of users. And like CPace provided that, the standard SPEKE did not, unless you make M and N a function of the user identities, which was one possible. But as I said, in terms of security, they all have similar properties. And I think the decision came down to several other aspects, like side channel security, and if like the exact details, how efficient they can be for different, if you work on different curves. And eventually, CPace, taking those things into account, was chosen as the winner of the competition. Finally, to conclude this talk, I would like first to mention that usually when you talk about the PAKE schemes, there are several aspects that one should consider. For instance, standard versus UC security. Certainly, UC security provides stronger guarantees, but in practice, sometimes it turns out to be the protocols turn out to be slightly less efficient. For what we saw, for instance, in the CPace or SPEKE case, is actually you can actually provide show that they achieve UC security, but they only achieve this further notion of the UC security if you assume that there is an explicit key authentication right after the protocol. J-PAKE was able to achieve that even without the explicit key authentication, but J-PAKE already had a few more rounds to start with. Second, most of these protocols don't deal with adaptive security. Only recently that we've showed adaptive security for the CPace case, but adaptive security is more realistic, but it's not always. Sometimes it has an impact on the efficiency. Fortunately, in the CPace case, it was not the case. Finally, augmented PAKE is something to consider in practice, because especially if somebody breaks into the server and if it's able to recover all the passwords in the clear, this would be an issue. So if you use an augmented PAKE, at least if somebody breaks into a server, that person would still have to use an offline part to be able to recover the passwords. And hopefully for those people who chose passwords with high enough entropy, they would be protected in that case. Finally, just some final remarks, that the design of PAKE protocols can actually be tricky, and sometimes they may seem secure, but one small change to it can make the protocol insecure. So the only way that I would say that one should be rely on this schemes on this to make sure that they're secure is to accompany the protocol with a clear explicit security proof, which usually when this is not the case, often you can be surprised and end up finding out that the protocol is actually insecure. So in terms of what is the correct model for PAKE? Like as I said, there are two, the most common models in the literature is the game-based model and the UC model. I think right now I consider the UC model to be the best one, because it provides stronger guarantees, like it doesn't make any assumption of the distribution of passwords, for instance. And second, finally, PAKE remains an active area because, as I said, there are still a few schemes that are being proposed that sometimes you have to analyze, you end up attacking them. And second, even for schemes that are out there and for which you already have a proof, sometimes it's interesting to see if you can improve the proof of security to make sure that they satisfy the strongest possible security notion. And this is something that has been happening more recently. And as I said, providing, if possible, and always aiming for better efficiency and stronger security guarantees. One thing that I did not mention here is that, another interesting open area is to consider post-quantum security, because a lot of the schemes so far that I considered here, they're all based on discrete logs, and they certainly would not be secure against quantum computers. So definitely, it's there are things to be done. Thank you.
Okay, yeah, thanks, Michel, for the nice talk.